Hello and welcome again. Here we have a typical physics problem of a mass on an inclined plane being held up by a rope. What is the tension in the rope? Except this time we added another box with another rope. And what is the tension in the second rope? The second rope is in sequence, the second mass and rope are in sequence with the first, meaning it's being held up by the first mass. And of course, the problem wants us to calculate the tension in the rope at point A, up there, and point B. And also calculate the magnitude of the force the incline exerts on each box. So in this particular case, the first thing you want to do is collect all your data, everything you have values for. And what we have is, we have mass, well this isn't mass, this is weight. Whoops. Weight is equal to W1, which is also equal to W2. Theta is equal to theta. And the coefficient of friction, well, it's 0 because we have a frictionless surface. How wonderful. Now, the next thing you want to do is set up your free body diagram. For this particular case, you want to set up a triangle, put a weight on it, and make your X and Y chart. Then, remember that first thing you remember is that no matter where you put your mass on any type of inclined plane, the weight wants to go directly to the center of the earth. It doesn't matter how you set your angle. The weight just always wants to go to the same direction. Now what does change is the normal force, the force normal to the surface of the inclined plane. The normal force wants to point outward, right out here, outward from the inclined plane. And it points outward by way of, dependent upon what the angle of the triangle is, or the angle of the inclined plane is. The way we can set this up is, set your normal force negative, pointing downward here. And set your normal force to say equal to W cosine of the angle of the inclined plane. Again, all this is dependent upon the angle of what your inclined plane is. The next thing we remember is that this weight physically wants to slide down, right? Wants to slide down the surface of this inclined plane. So we say F sub S is the sine component of this right triangle we're creating. Okay? So now we have all the parts and pieces that we need to put this thing together. In terms of forces, summation of forces in the X and Y direction. So first thing we say is, what is the force, or what is the tension at point B right here? So that one looks like it's going to be easier to solve than point A. Point A looks like W1 and W2 are going to have a part in the tension in what's going on in point A. However, for point B, only W2 is going to have a play in this tension that's going on right here. So let's find that one out first. For point B, summation of forces, first of all, are there, if we have this triangle like that, or if we have this X and Y graph like this, is there any part of that rope at point B that's pulling in the Y direction, if our X and Y directions are slanted to accommodate the surface of the inclined plane? No, it isn't. It's all in the X direction. Point B is equal to, point B, summation of forces in the X direction for point B is equal to F sub S2, the sliding force of box 2, which is, as we remember, W2 sine theta, negative W2 sine theta. It's falling in the negative X direction with respect to this X and Y graph that I wrote right here. It doesn't have to be negative if you don't want it to be, whatever, but it plays out perfectly for adding the tension at B, right? So we say that T sub B is equal to W2 sine theta. All right, so now, what is the tension at point A? Again, like I mentioned earlier, the first mass, or the first weight and the second weight are both going to have a part in its tension. So here we say point A, F sub X is equal to negative F sub S1 plus negative F sub S2 plus the tension of the rope at point A. And if you remember, F sub S1 and F sub S2 Well, they're just W2 and W1, respectively, sine of their angles. So we say that TA is equal to W1 sine theta plus W2 sine theta. All right, we're almost done. Calculate the magnitude of the force the incline exerts on each box. So F sub y, all right? F sub y, what's the only thing happening there? The normal force, all right? The normal force is the only thing that's happening right here. And I neglected to write that, but F sub n for 1, the first box, is equal to W1 cosine theta and the normal force for 2, respectively, as you would guess, W2 cosine theta. Thank you very much for watching this video, and I hope you have a good day.